Welcome back, everybody. We are in the thick of it now with electric circuits, diving right in. So we talked about capacitors. Those are one component that you might find in an electric circuit. Today we're going to be looking at some of the other components. So first off, we need to get an idea for what an electric circuit is. So first off, the word circuit. I think electric we're pretty clear on. We're talking about charges when we deal with something that's electric. Circuit, you might have some experience with this, maybe with running. You might run circuits. This would be like running laps. Circuit also is is pretty close to the word circle, which might have some meaning with the electric circuits. In general, an electronic circuit or an electric circuit is thought of or is defined as a series of individual electronic components, like capacitors could be one of those. Other things might be resistors, transistors, inductors, diodes. So there's lots of different components that we could use. But a series of these components that are connected by conductive wires or some other conductive material. Wires is usually what we use, though. Such that electric current can flow through those things. So if I were to draw a really simple electric circuit, the simplest one that I could think of here would be a battery with a plus side and a minus side here. And we're going to connect that battery to something, some electronic component. And then our wire, so these lines here represent the wire. Our wire goes back to the negative side of the battery. And so this is going to allow electrons to move through this wire. The electrons are moving in this direction. They go through whatever this thing is and toward the positive end of the battery. They're pulled that direction by these positive charges that exist here. Now, I think it's worth noting at this point that by convention, we actually talk about electric current, which is the flow of charges, as being from positive to negative. So in this direction, this is I, and I is electric current. So this happened as a result of a lack of knowledge about the structure of the atom and the idea that it's the electrons that are doing the moving when we first started developing terms and quantities to describe electric circuits. So they picked the positive charges as being the ones that are moving, and it turns out they were actually wrong here. It's the negative ones, it's the electrons that do the moving. But just by convention, we've kept that system. It doesn't really matter here whether we think of negatives as moving this way or positives as moving this way. We're going to get the same results either way. And so our electric current flows from the positive end of the battery to the negative end of the battery. And so the battery, it serves as, the main function it serves here is to make sure that this end stays positively charged and this end stays negatively charged. And it does that by using these chemical reactions that produce positive and negatively charged ions. So that gets into how batteries work. We're not going to really go into much depth with that. But then this current, it's passing through some component here, and we're powering that. Now, probably the most common component that we'll be using in these circuits is drawn out like this. And so these drawings that I'm making, we call those schematic diagrams, or circuit schematics, or circuit diagrams. So we have our battery here, and then when we just have a squiggly line in there, that we call a resistor. And the resistor does exactly what you would think it does. It resists. Well, what does it resist? It resists the flow of electrons here. So we might think of this in terms of a pretty common analogy, the water analogy. Let's say we have 2 tanks of water. And we put one up high and another one down low. And these have water inside of them. and then we're going to let some of the water pass through this opening right here, and we'll have it come down to our lower tank. So we're going to have a net flow of water downward. Okay, so we'll open this up, and our water starts to flow downhill. There we go. So from this area of higher gravitational potential to an area of lower gravitational potential. And then we have at this bottom tank, or in between the top and bottom, we have some device that's capable of moving the water back up. So some kind of a pump. And so the pump is going to move water back up to our top tank. So that's like the battery here. Now, if we looked at some point along this this path, and let's say we put a blockage in there. So we restrict the flow to just a little bit of water going through here. Okay, so just a little tiny area through which the water can flow. That has the effect of slowing down the water, or decreasing the amount of water that can go from the top tank to the bottom tank in every second. And it slows it down at every point along the path here. So it's not just at this one spot that water gets slowed down, because if it were going fast through here and then slow through here, then we'd have a buildup of water right here, and we can't have that. Our water only has so much space it can occupy. So our water gets backed up all the way through, and it just kind of trickles through here. So this is like our resistor in the circuit up here, except instead of resisting the flow of water, it's resisting the flow of electrons, or it's resisting the electric current. So we need to have some idea for what we're talking about with electric current, and then how this fits in with resistors and other electronic components. So electric current, first off, is a lot like water current. So current, we'll say, is the rate at which electrons flow, or the rate at which charge moves. And so in general, we'll say I, the current, is equal to the amount of charge that moves from one place to another, so we'll say that the change in charge, divided by the amount of time it takes, and that's going to be in seconds. The charge will be in coulombs. So the units on current would be coulombs per second. Or we abbreviate that. We have another unit that we use for that called the ampere, or sometimes amp, abbreviated to amp, or sometimes just a capital A for the flow of charges, or for the electric current. So this, like I said, it's just a rate. And if we go back to this situation where we put some kind of a resistor in here that slows down our current, or that decreases the rate at which charges can flow through this whole series, or this whole circuit, then our current decreases. Over here, we could see our current would decrease in this situation too. The amount of water that can make it from the top tank to the bottom tank for each second that goes by, it decreases when we have this blockage in our pipe that restricts the flow, just like the resistor restricts the flow of electricity. Now it turns out that that the amount of current that we can get through that resistor, through that circuit in general, depends not just on the amount of resistance that we have there, but also on the potential difference, or the voltage, between those 2 points. So if we redraw this quick, got our plus side and our minus side, and let's say this is a 1.5 volt battery. That means there's 1.5 volts of potential difference between this spot and this spot. and then we pass our current through a wire and through an electric, or through a resistor here. The amount of current that we have going through this whole thing, I, the amount of current, is going to depend on this value, which we call R, the amount of resistance that this resistor has. So R is resistance. And it depends on the voltage of this battery. So remember, voltage, or potential difference, that's how much work we're doing on each coulomb worth of charge as we move it around. So we go from high potential to low potential, and then this battery, it essentially lifts these charges back up to high potential. It's really a more complicated relationship going on there. The charges don't quite flow through the battery in that way, but it's a good enough analogy for us. So it lifts them back up to high potential, and then they fall back down to low potential. And so if we have a really high potential that we get lifted to, so instead of a 1.5 volt battery, that's like a AA or a AAA, let's say we use a 9 volt battery. That's like the square ones, but I'll just leave it drawn the way it is. So now we have a lot of work we're doing on this. We get the electrons up to a really high potential, and so they have a lot more oomph to them. They have a lot more push from this battery to get them through here. And so with that extra voltage on the battery, the current is going to flow more. We're going to have more current. The charges are going to move more rapidly through this system. And then if the resistance were to increase, then that's going to slow the current down. So we can see here that I, the current, is directly proportional to V, and I is directly proportional to 1 over R. So as V increases, as the voltage increases here, this is V, the voltage, we'll see that the amount of current flowing through this system increases as well. As R increases, we'll see that the amount of current decreases. And so in general, we can write that the amount of current is equal to V over R, the amount of voltage divided by the amount of resistance. And this is known as Ohm's law. And it's actually written in a different form on your equation sheet. We multiply both sides by R, and we get V equals IR. That's how Ohm's law is written on your equation sheet, where V is the voltage, and I'll just put it in volts. I is the current measured in amps, and R the resistance. We haven't talked about units for this yet. The units for resistance are ohms. And so that relationship is going to hold true. Resistors typically have a fixed value regardless of the voltage or the current. And so once we know that value, we can figure out if we know volts, we can find amps. If we know amps, we can find volts.